Welcome to the lectures on fundamentals of MIMO wireless communications. Now, since we have studied the properties of the channel, that is the flat fading channel, then the frequency selective fading channel, then the space selective channel, we have seen the statistical properties of H, which is the matrix relating the multiple input to the multiple outputs. We have seen how it can be factored into its eigenvalues and singular values. We have also seen that there is a distribution of the joint distribution of the eigenvalues. We have also seen there is the distribution for the minimum eigenvalue. So these will be handy when we carry forward with our discussion. We have also seen the moment generating function for Frobenius norm of H, and we have always said that these are random variables. So again, the moment generating function would be useful. So now we are at a time where we can start our journey into understanding the different communication techniques which take advantage of the spatial mode of the channel. So usually the study is can be looked at from the point of view as spatial diversity. So we have spatial diversity to study, and the other thing we have is spatial multiplexing. These are the two very important things in MIMO communications. Of course, there are beamforming and other things, but these are primary based on which many things evolve. So we will start our discussion with diversity, and then once we are complete with this, we will move on to multiplexing, and then we will have a discussion on diversity multiplexing trade-off. That means given a set of number of multiple antennas, how can we get diversity gain and multiplexing gain, or maybe part of one, part of the other, or simultaneously both. Those are some of the things which are important. So in some cases people do study spatial multiplexing to begin with. However, we'll take diversity because that's most straightforward, that comes directly from your understanding of wireless communications, and then a little bit more advanced topic is spatial multiplexing. So that's how we will proceed. So when we look at diversity, diversity is basically spatial diversity. So spatial diversity is we have the input side and we have the output. So when I say input, that means the transmitter. We have the transmitter side enabled with multiple antennas. We have the receiver side, which is enabled with multiple antennas. So that's the transmitter and the receiver. So as we have seen that we have many channels. The first kind of channel is the seesaw, where single input, single output, which is studied in classical wireless communications. Then you have a single input, multiple output. We have seen how to write these kind of channels. Then we have multiple input, single output. We have also seen how to write these expressions, and then finally we have multiple input, multiple output. So our aim would be to understand how to get diversity gain out of all these different modes of operation. Seesaw mode of operation is what we will not see very explicitly, but that can be covered anyway. So we'll basically look at how do you extract diversity in this direction. So when we study spatial diversity, you have the option of doing, when I say single input multiple output, we mean to say that you can obtain diversity at the receiver side. Multiple input single output means you can do diversity at the transmitter side, and MIMO means you will be able to do it on both the sides. So when you do at the receiver side, things are relatively easier, but the moment you have to do anything at the transmitter side, there are two possibilities of doing them. So when you do processing at the transmitter, one is you may need a feedback of channel information. That means H, information related to H, has to be fed back. There could be another mode of operation where no feedback, and this is very, very interesting, because when there is no feedback, the interesting part is you can keep on transmitting without waiting to get the channel information at the transmitter. Our aim would be to cover these different aspects of communication in this. So, let us get into the study of spatial diversity. So, when we talk about diversity, when we use the term diversity, this is not very new to communications. When you do wireless communications, the different domains that you access are time domain, frequency domain, and finally the space domain, right. We have seen the channel can be described, channel has its variability in the time, where it is slow or fast fading, it is variability in frequency, flat or frequency selective, it is variability in the space, that is rich or poor scattering. So, we are not referring to that currently. We are of course, that is very critical, but currently we are talking of obtaining diversity from time domain, frequency domain and space domain. What I mean by this is that a diversity can be obtained in time domain, it can be obtained from frequency domain, and finally, it can be obtained in the space domain. Before we launch into the space domain, let us briefly take a look at what is the meaning of diversity. By diversity, what we mean is that when I have sent a signal into the air, I would like to receive multiple copies of the signal at the receiver. So, when we receive multiple copies, we could receive the copies in time domain, we could receive them in frequency domain, and we could also receive them in the space domain. So, before we go to space domain, when we talk about time domain, when I would like to receive them in time domain, suppose I would send x of t. If I would send x of t, I would like to receive x of t, which I would write it as x cap, let us say, at a time t, and I would also like to receive x cap at a time t plus tau. So, once I have multiple copies of the signal, then I can do something. We will see what we can do. When I talk of frequency domain, suppose I get write capital X as the frequency domain information of t. So, if I would send it at a certain frequency f, I would like to get it at f as well as at x of f plus some spacing, let us say delta f, right. We will describe the space domain separately. So, in time domain, things can be, one can imagine that I have I would receive the first delay version of the signal at tau 0, I would receive the replica of the signal again at tau 1 and so on and so forth up to tau n, that means the maximum delay. And if these signals are uncorrelated, that means x at delay t 0, x at delay tau 1, x at delay tau n, if they are uncorrelated, then we can get some benefit out of it, simply because if you remember the way we write, if I say y of t is the received signal, and what I get is basically h convolution with x, okay, plus noise. Okay. So, I would be receiving multiple copies because of this convolution, and if these copies are uncorrelated, scattering, then I could take advantage of it and do certain things. There are methods of doing it. If it is flat fading, that means if a flat fading means all these are at the same delay, then still you have multiple paths. The signal does come from multiple paths, but since the delays are the same, they would appear at the same time and we cannot separate them. They are appearing at the same instant of time. So, in order to get multiple copies, I would have to send x at t 1, and I would have to send the same x again at a time x t 2, right. So, that means I am using 2 instants of time to receive 2 copies. If I look at the frequency domain, again if there is the spread in the Doppler frequency, I would receive the signal at f and I would again receive the signal at f plus delta f. Whereas, yes, and if there is frequency selectivity, then also the signal, the copy of the signal I receive at f and the copy of the signal I receive at f plus delta f are again uncorrelated. but in the frequency domain rather I have to send a signal at a frequency x f1 and a frequency at x f2. That means I will be sending the same signal at two different frequencies and I will be receiving them. So, what we see from here, that means I am sending at two different time and I am sending at two different frequencies. That means I am using time t1 and time t2, or I will be using frequency f1 and frequency f2 to get two copies. So, in wireless communication we all know that the time and frequency resources are very costly, and that is the spectrum basically. So, we would like to make a maximum use of it, and there are different ways of achieving diversity gain. So, if I am going to use this particular method, that means use replicated transmission in the time domain or replicated transmission in the frequency domain, I am using more than one resource of time or frequency to send the same information. There could be smarter ways of doing it. So, this could be one of the possibilities, but may not be always recommended. So, this is valid, but whether this one is to be used or not is a secondary question. You may be aware of forward error correction codes. In short, it is written as FEC, that is forward error correction code. So, in forward error correction code, usually parity bits are added. That means we are having a sequence of bits, and then a new code word is formed. So, if I have, let us say 3 bits and 2 bits of parity are added, I generate a new code word which is 5 bits. So, when we have this 5 bits of information, so instead of sending 3, I am sending 5 bits. If it is a very plain and simple system, I will be using 5 bit durations. So, previously I was using 3 bit duration. That means, let us say I have 3 bits to send, I add 2 parity bits, then I get 5 bits in total. So, previously I was using 3 times each bit duration indicated as TB. Now, I have to use 5 times the bit duration. So, I am actually using extra time and I am spending some of my time resources. So, it is costly, but this is of course necessary, and the other advantage is we need not necessarily send this in time domain. There could be many different ways of doing it. If we are using higher order constellation, then probably all these bits could be easily captured into one symbol, and we can send them out, so without losing time. And we could also distribute them over frequency, and we could also gain benefit out of it. And lastly, if you are using very long code words, then your efficiency is very large, and in that case the loss due to the parity would be significantly less. So, this is another mode of getting some gain, but it is somewhat related to this diversity gain that we will be discussing. So, going beyond this, if we look into the spatial dimension, if we look at the spatial dimension, suppose I have one transmit antenna at the transmitter side. I am drawing this as the transmitter, and in a typical single input single output system, I will call this as the receiver. So, when the signal goes out to the receiver, let us say x of t, it is easily received as y of t at the receiver. And if I would draw on the x axis, let us say this is time, and this is the gain of the received signal strength, let us say y of t mod squared. Let us say we do this, and what do we expect? And let's assume, okay, on all cases we will be assuming flat fading, and we will be also assuming slow fading. Unless otherwise mentioned, these will be the prime assumptions. So, with time I am going to get fluctuation of signal strength, which is random. We have already discussed this. If it is Rayleigh distributed, then this will be exponential distribution. The envelope squared would be exponential distribution. We have also discussed about the variability being captured by Doppler, the coherence time, and all kinds of things we have already discussed related to this. Now, we have also discussed that there is level crossing rate. If there is a certain threshold, the rate at which it crosses the threshold. We have also discussed there is this average duration of fade when signal goes below the threshold. So, we have actually talked about this, indicating that these are performance metric, means if it goes below a threshold, there is outage, and what we usually define, of course, other than BER, probability that the SNR, received SNR as a function of time, or received SNR, I can, the received SNR is less than a certain threshold. Yep. So, if received SNR is less than a certain threshold, what is this probability? So, we would like to have this probability as low as possible. That is one of the desired things. So, if we want this probability to be low, what you usually do is, instead of sending the transmitted signal by the way we have drawn it, we would like to increase the level of the transmit power, so that the received signal strength is something like what we are drawing here. So, that means if I push the transmit power, the received power increases. So, instead of the blue one, whatever is the new line that we have drawn is what we are going to get. And if this is my threshold, that means this gamma TH, then what we will see is that since I have increased the transmit power, average transmit power, there is hardly any probability that the signal goes below this threshold. So, we are reducing the probability. So, that means we are able to, we are actually giving a margin. Margin is by means of transmitting extra power that we are able to achieve this condition. Whereas, now instead, let us look at the situation that we have another receive antenna. This is antenna 1 and this is antenna 2. So, we can use a different color for this. Let us say this one, it may not be so clear, but this is green in color. So, and the same signal will now be received in antenna 2 as well. I have not sent any multiple signal, we have sent x of t, or according to our earlier description, s tilde of t in the baseband equivalent or the low pass equivalent signal. Whatever was received here, I would receive another copy of the signal, right. This is very, very clear, because there are reflectors around, and we would be getting scattered components. We will use the narrowband antenna array assumption. That means the signal here remains the same, except there is a phase shift. So, yeah, so basically with this, whatever signal I receive here, let us say in the first antenna we receive the signal y of t or y1 of t, whatever we are going to receive in the second antenna, we could write it as y2 of t. And if this distance of separation, is let us say some delta x, let us say this distance is delta x. What we have studied when we studied the channel in the spatial domain, we said that if delta x is less than the coherence distance, then the signal received in both these two antennas are correlated, whereas if this distance is greater than the coherence distance, they are uncorrelated. We have also seen that when signals arrive from all directions with equal probability, that means when p of theta is equal to 1 by 2 pi, we have studied this case, we have seen that the correlation is a function of j0 2 pi delta x by lambda, and this leads to, that means if I look at the mod squared of the signal, what we have find is that at a separation of lambda by 2 approximately, that means we have found it to be 0.38 lambda, the correlation goes to 0. That means decorrelation distance is lambda by 2. So, if this separation is more than lambda by 2, let us say if it is comparable to lambda by 2, the signal received here y1 and y2 would be uncorrelated. In that case, we can tentatively draw a received signal. I will take that blue one is the transmitted signal. We could take a uncorrelated signal coming in at that place. So, what we can see is statistically the blue and the green signals, that means received by antenna 1 and antenna 2, they appear similar. There is the same threshold, signals go below the threshold, right. The average is more or less the same, but now if we take both these signals simultaneously, and for instance, although this picture is getting a bit cluttered, we'll use one pink color. So, suppose I'll use a thicker line. Yeah. Suppose we devise a method by which out of these two signals, that is y1 and y2, we select the best of the two. That means in this part of the time we select the blue one, in the next part of the time we select the green one. Next, when blue is high, then green, then blue, then green is high. We are riding the crest. Blue is high, then green is high. I am just following whichever is highest. The blue is high, green, blue, green, 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 blue, green, blue, green, and so on and so forth. So, this is the signal that I am going to get if I select the best out of the two. So, that means if I carefully study this situation, we are receiving signal at antenna 1 and also receiving it antenna 2. We have not used the extra power. That means we have not done what was done during the red color. So, we have kept the same average power as earlier, but whatever is received here, the same average received signal will be here. This is because of stationarity. That means within the coherence distance, within several tens of coherence distance, spatial distance, which is within a certain region, the homogeneous channel assumption. We had made the homogeneous channel assumption. Basically, we had made wide sense stationarity, uncorrelated uncorrelated scattering, and homogeneous. This is the assumption that we made. The average received signal strength is the same in a certain area. Then what we see is that even though these individual links, the blue link and this green link, they go below this threshold, whereas this pink color, which is riding the crest of them, which is taking the best of the green and the blue, is hardly going below this threshold. There might be occasions, but in this particular diagram we do not have it. So, what we see is that by virtue of getting independent signals in these two branches, there is a possibility that the probability received signal strength goes below the threshold becomes very, very low. We can make it very, very low. So, this is in short what you can say the advantage due to diversity, and in this case we are not using extra time, we are not using T1 and T2, we are not using F1 and F2, right. We are not using extra power. The transmitter is sending at the same power PT. We have not increased the power simply because we have used another received antenna. This is at no cost to the spectrum, no cost to the power at the transmitter. We have been able to improve the performance. The cost, of course, nothing comes for free. So, there has to be a cost that is paid. So, the cost that is paid over here is receiver complexity, because each of these branches, these branches, this blue and these green branches, these are all separate branches. So, when these two branches are separate branches, they have their own receiver circuitry. They will have their own receiver circuitry. So, your receiver cost, the receiver cost would go up. That is the penalty that you are paying for this. Otherwise, nothing else, and receiver cost is going to go up, and along with that, because the complexity is up, what you can also guess is receiver power consumption would go up, simply because you are processing at more than one branch. This is called a branch. This is one of the receive branches, is another receive branch. So, you have to do processing with as many branches. So, if there are MR antennas, your signal processing cost goes up, at least in the RF section. Baseband section complexity would be different. So, at this cost, at least you are able to get the signal out of the deep fade conditions where there was a single antenna that is used. So, this is the prime motivation that we go for diversity. Now, in the case that we place the antennas which are not separated by coherence distance, that means suppose we place an antenna which is somewhere in between and which is not less than the coherence distance. In that case, the signal will be correlated, but we have to find certain combiner technique There would be combining techniques at the receiver. So, we have to use certain combiner technique, and still you could get something extra. The fundamental reason why this is happening, if you have to understand intuitively, the moment I add an extra antenna, the moment I am adding extra antennas, what I am doing is effectively capturing more energy. This is one intuitive explanation. That means, suppose I have a signal, suppose I have a radiator, it is radiating some signal. Receive antenna is having a certain size. If I put one more antenna, it is capturing a little bit more of the surface area. If I put another antenna, it is capturing a little bit more of the surface area. So, I am capturing more energy. Now, when I do this, then I have to combine the signals in such a way that I can take advantage of it. This is an intuitive rough explanation of what is happening. So, for this there is no change in the transmitter configuration, only the receiver configuration changes, and we can get benefit out of it. So, this is the basic motivation for using receive diversity. We can do a similar technique at the transmit side, and that we will see, of course, at a later time. So, with this we start our journey into finding the quantitative gains that we can get out of such signal processing techniques using spatial diversity. Thank you.